Okay, so here I'm going to introduce atomistic spin models and the essential fundamental physical foundations of them. So in magnetic materials, the magnetic properties are actually linked to the intrinsic electronic structure, so essentially the formation and densities of electrons within the actual solid. This gives rise to natural physical phenomena such as magnetic moments, exchange interactions, and magnetic anisotropy. So some of you may be familiar with larger scale simulations through numerical micromagnetics, where typically you take a small volume of space and then you assume that all the magnetic moments within that volume are aligned, and then you have a sort of a macrospin moment that you then evolve in time. And this gives you, a kind of a good approximation to the material at larger length scales of up to hundreds of nanometers, maybe a few micrometers in size. So atomistic models sit between these two kind of extrema. So on one end we have the electronic structure, which gives you the fundamental interactions in the magnetic material, and on the other end you have micromagnetics, which can calculate things such as dynamics and domain walls and other kind of macroscopic phenomena. So in this case, the atomistic model sits between these two and kind of has some advantages of both. So it essentially takes in the interactions from the electronic structure, and then also enables you to calculate dynamics and other magnetic properties. Okay, so atomistic spin models. How do you kind of go about understanding what they are? So the fundamental approximation in an atomistic spin model is that essentially you have a localized magnetic spin. So in a magnetic material, you have quantum mechanical spins which obviously precess around some quantization direction, in this case Z, where you essentially have a magnetic angular momentum associated with that spin. Now, as a quantum mechanical entity, you can't actually resolve all three components of this spin at any one time due to the Heisenberg uncertainty principle. So here actually we only resolve the one component of that, while the in-plane components are undefined. And it's this quantization vector which defines the direction of a localized magnetic spin, which we then call S. And this typically has dimensions of a few Bohr magnetons. In reality, of course, the material is somewhat itinerant, and so you have a natural imbalance in the number of d electrons that you might have, and so the spin magnetic moment tends to be a non-whole number of Bohr magnetons in metallic systems. But this is the fundamental approximation of the atomistic spin model, that essentially at each atomic site you can have a local spin density which is semi-localized. For cobalt and iron, this is a reasonably good approximation. For nickel, less so. Obviously for oxides, where you have genuinely localized d electrons, then again this is a good approximation. So for a large class of materials, this localized moment approximation is actually not bad at all. Okay, so while that's the kind of fundamental assumption, if you like, in the atomistic model, we still need to be able to write down the energetics of the system. So to do this, we actually use something called the spin Hamiltonian, H for short, which essentially writes down the energy contributions in the magnetic system. It's called a spin Hamiltonian because we throw away other terms that are not magnetic, for example, potential energy, kinetic energy. We're simply not interested in the motion of electrons in this way, and hence we have something called the spin Hamiltonian. For most materials, we consider three main types of interaction. The first is the exchange interaction, which couples neighboring or nearby atomic spins in parallel or anti-parallel directions, and this is the strongest term in a magnetic material. We also have magnetic anisotropy, which allows the moments to align in preferred crystallographic directions. And then finally we have some interaction with an external stimulus, for example, an external magnetic field. The foundation of the atomistic model is the Heisenberg exchange interaction, which essentially tells you how much the energy varies as a function of the relative directions of two neighboring or nearby spins. So using kind of a finger model, which is common in atomistic simulations, we can consider, say, two neighbouring spins. In this case, when they're parallel aligned for a ferromagnetic system, then this would be a low energy state, where the spins are kind of in energy minimum. If I then rotate one of these spins round, this would then be a high energy state. So essentially, the dot product of the spin directions gives you the energy cost of misaligning those spins. And technically, in a bulk material, you would have a summation over all the nearest neighbours in the system and maybe further apart in other type systems. So hence we have this summation over all the exchange interactions. So this Jij is the strength of the interaction of all pairs of spins for I is less than j. Of course, if you have two spins, you actually have two interactions. The first one is from this spin to this spin, and similarly from this spin to this spin. So you actually count the interaction twice. So you can either have a half in front of that double summation, or you can only count I to j, not j to I. Hence why I is less than j is the limits of the summation. Okay, so the sign of this exchange interaction, Jij, tells you whether you prefer either ferromagnetic ordering, where all spins prefer to align in parallel, or antiferromagnetic ordering, where spins prefer to align antiparallel. Typically, this interaction is the strongest interaction in a magnetic material, and it gives rise to macroscopic magnetic order. So, usually to measure something you would need anisotropy as well, or a strong applied field, but this actually tells you whether material is fundamentally magnetic or not. And this tends to be 1,000 times bigger than the next largest contributions for most relevant magnetic materials. The fundamental quantity that kind of gives you access to how big the exchange constant is therefore the Curie temperature, or the temperature at which the magnetic order disappears. This is kind of characterized by a mean field expression given here, which relates the fundamental exchange energy to the thermal energy, so Kb times the Curie temperature, divided by epsilon, which is a correction factor for spin waves, and also Z, which is the number of nearest neighbours. So essentially, the total exchange interaction Z times Jij would then be proportional to the Curie temperature. So if you know the material properties, for example, whether it's the crystal structure and the Curie temperature, then you can infer an approximation to the strength of the exchange interaction. The epsilon factor is essentially a correction to this mean field term. The details are given in this paper by Dmitry Garanin in 1996, where he derives for a number of different range of Hamiltonians and crystal structures what this epsilon factor is. It's approximately 3/4, but it depends on the crystal structure and the range of interactions and so on. But this gives you a kind of a very simple way to define the exchange constant and from a macroscopic parameter that you have relatively straightforward access to. Of course, if you have access to ab initio methods, then you can also use those to calculate, for example, range-dependent exchange constants and give a much better approximation to how those vary as a function of interatomic distance, for example. So the second term in the Hamiltonian is typically the magnetic anisotropy energy. So this can have many different origins. Historically, it would be called magnetocrystalline anisotropy, which means it relates to crystal symmetry. But in the more modern sense, it's more general because you have contributions, for example, from interfaces or from defects or strain. So there's also kind of fundamental physical quantities that give rise to magnetic anisotropy, not just crystallographic structure. The two most common that you might come across are both uniaxial anisotropy and cubic anisotropy. For uniaxial, the magnetic moments prefer to align along a unique axis. So essentially, if I, for example, had a magnetic anisotropy along the z-axis, then it means that all my little atomic spins in my system would prefer to align either on the plus z direction or on the minus z direction. If they lie within the plane, so for example in the x-y directions, then this would be a higher energy state. So we can kind of write this down as some dot product of our spin direction with some easy axis vector E. So again, then the energy then varies. If this is aligned, then this is low energy state. Similarly, if it's anti-aligned with this axis, it's also a low energy state. while all directions perpendicular to that would be a high energy state. Typically the anisotropy here is characterized by a constant Ku, which tells you how much energy it costs to rotate the spins from this direction to from the easy axis rather to the perpendicular direction. The other common form of anisotropy that you might find is cubic. So this is typically seen in bulk crystals of iron or nickel, for example, but also in other structures, for example in magnetite, where you have a strong kind of cubic symmetry to the crystal. There are multiple different forms of actually writing this down, but for computational efficiency, we actually use this form here, which is some simple power expansion in x, y, and z components of spin. Note that the sign is positive in this case because of the conversion from the usual cosines that you might otherwise see. And here the Kc is then the cubic anisotropy constant, which again is an atomic level constant. Finally, we have external magnetic fields. So this essentially then just gives you some way of stimulating or manipulating the magnetic structure of your system. And the coupling of this is essentially given by the product of the spin moment and its length with the applied magnetic field direction. And essentially gives you a preference or a low energy state when the spins align with the applied field direction, and any other state is a higher energy configuration. Okay, so now we've defined the spin Hamiltonian. That essentially writes down all the energy terms that we want in our Hamiltonian or in our system. And so while that's fine, we can write down all the energies, it's not particularly useful because we can't determine how the system varies in time. So integration methods allow us to calculate macroscopic properties that otherwise would not be available just from a kind of writing down the Hamiltonian itself. So although perhaps not considered one, the kind of origin of dynamics actually came with the Ising model. From 1924, which is almost 100 years ago. So at the time, this was an analytical model of actual phase transitions and how that might occur in a magnetic material. Of course, in the 1970s, 60s and 70s, this then developed into a numerical model where you could actually then evolve a system of coupled Ising spins to see how the magnetic properties varied, for example, with temperature or with time, in comparison to this simple, or not so simple, analytical framework. So this could be regarded, if you like, as a toy model of magnetic material. It's toy in the sense that you have an infinite anisotropy because you have a global quantization axis for all spins. So essentially spins can only take two states, spin up and spin down, which is a kind of a coarse approximation to the real nature of magnets, which of course can rotate with magnetic fields and can also have domain walls and so on. But nevertheless, it gives you the fundamental magnetic properties of the material, and for example, how temperature effects lead to a phase transition from a ferromagnetic state to a paramagnetic state, and so on. So although they have their place, typically for real magnetic materials, this is an excessive approximation, and so not particularly realistic. So for the Ising model, as I mentioned before, we have two states, essentially spin up and spin down, and we can then describe the energy difference between these two states based on only the exchange interaction between the spins. So again, if the spins are ferromagnetically aligned, that's a low energy state, and if you flip one of the spins, then that costs you exchange energy, and so at low temperatures, typically the ferromagnetic state is preferred, while at high temperatures, above the Curie temperature, then you get this paramagnetic state where the spins will flip because the thermal energy is much larger than the exchange energy. To integrate this in time, we typically use then a Monte Carlo algorithm. So essentially the idea is that you pick a particular spin, a random spin in your system, and you try a new trial state for your system. So in this case, we can pick one spin and we can flip the sign of that spin. We can then evaluate the energy from our spin Hamiltonian before the spin flip and also after the spin flip. This energy difference then can be used to simulate the effect of thermal fluctuations of the spin system. And essentially then we accept the probability of this change of state by exponentiating the change in energy over the thermal energy of the system. And this then will give you a Monte Carlo move. So if kBt, for example, is very small, then this probability of flipping is very, very tiny. As the thermal energy gets much larger, then the probability of flipping increases, and so you get a kind of an evolution, or natural evolution of the system in time. Of course, for a realistic system, where the spins can have any direction in space, then you need to allow that to happen. And the fundamental algorithm is always the same. You pick a spin, you change its direction, and then compute the change in energy. But here we have a combination of different trial moves to allow the spin to explore the full 3D phase space. So this can be a combination of spin flips, where you reverse the sign of the spin. You can also have a small variation. So if your spin is, say, along one particular direction, you could then look at small angular changes of the spin within that vicinity, or kind of a cone. Or alternatively, you could look at a random direction of spins in all 3D space. Now, typically at low temperatures, these small moves, so part B here, give you a kind of a more realistic exploration of the local energy surface, while the spin flips and random moves tend to be higher energy, but also allow you to evolve, for example, things like hysteresis loops more quickly. So typically you can use a combination of these different trial moves to efficiently explore the phase space of your system. More recently also we developed an adaptive algorithm which actually follows again this kind of localized move but with a variable trial width. And the idea there is to try and optimize the exploration of the phase space to make the acceptance probability as high as, well, approximately 50%, so that you only reject about half of the moves, which means that you make an efficient exploration of phase space within a reasonable number of Monte Carlo moves. And it turns out that this is the most efficient way of evolving the system with a Monte Carlo algorithm. The other main method for evolving the system in time is using atomistic spin dynamics. And here what we do is we apply the Landau-Lifshitz-Gilbert equation at the atomic level. So now rather than considering a block of spins and you assume that all those spins are aligned in parallel, we now apply the same equation of motion to individual atomic spins. This equation is made up of two key components. The first is the precession term, which SI cross B, which essentially forces the spins to precess around the field direction. So for example, in this diagram, the spin would prefer, well, the field is along the Z direction, say, and the spin will precess in this manner around that field direction. Second term is a relaxation term which over time allows the system to lose energy and essentially to align itself with its net magnetic field. The first term has origins in quantum mechanics in terms of the precession of the spins, while the other term is phenomenological in the sense that it provides some coupling to a heat bath to allow the system to relax, but the derivations of that are more complex in terms of fundamental interactions or electronic interactions with the system. The critical parameter in this is actually called the Gilbert damping parameter, which here we denote as lambda I, and this is essentially a coupling to the heat bath. So the stronger the damping, the faster the system relaxes to the field direction. So metallic systems typically have values 10 to the minus 2 to 10 to the minus 3. In oxide systems, you may get down to 10 to the minus 4, for example, in yttrium iron garnet. Some high anisotropy materials, for example, iron platinum, may have larger values, maybe up to 10 to the minus 1. There are ab initio studies which will allow you to extract this lambda value, but typically we use that as a phenomenological parameter based on either experimental data or some other dynamic measurements. Of course, the Landau-Dirichlet-Gilbert equation is fundamentally a zero temperature equation of motion. And so what we want to do is include temperature effects within our simulations. So to do this, we use the stochastic Landau-Dirichlet-Gilbert equation. So this takes the ordinary Landau-Dirichlet equation and then adds on a random thermal field to simulate the fluctuations or thermal fluctuations of the spin in time. So the effective field then comes from this random thermal noise plus the derivative of the Hamiltonian with respect to S. The 1 over mu I here is a unit factor conversion to make sure that our fields are all in Teslas. And the random thermal noise has these statistical properties that the width of the distribution is proportional to temperature and the damping constant to ensure that the equation of motion obeys the fluctuation dissipation theorem, and the noise is uncorrelated in time and space. So essentially we have a white noise approximation. It turns out that this is not necessarily a exact approximation, but for metallic systems at least, the correlation of the noise is probably going to be around about a femtosecond or so. So roughly equivalent to the time steps that you would typically use in the Landau-Dirichlet-Gilbert equation. So here we have an example of the relaxation of a spin. So the spin started along the x direction and then relaxes up to the field direction given by the grey arrow. But you can see now that the thermal fluctuations then excite motions of the spin to kind of simulate those thermal effects. So while the spin prefers to align along the field direction, there's some constant thermal noise which is exciting spin waves away from that. So if you want to picture in your mind of kind of what an atomistic spin model is, it's a magnetic analog of molecular dynamics, where in molecular dynamics you have atomic positions and your atoms move about in time and space. The equivalent is that in the atomistic spin model, lattice points are actually fixed, but the spins themselves, again, follow deterministic equations of motion, and so you can then model the dynamics of the system. One of the difficult factors with the Landau-Dirichlet-Gilbert equation is that the time step is relatively small for these atomistic models, and the reason being is that the exchange interaction is extremely large. And that leads to very fast dynamics when you look at individual spins and how they evolve in time. Therefore, depending on what temperature you're running your simulation at, you may need quite low time steps down to 10 to the minus 16 seconds or 0.1 femtoseconds. If you're far from TC, for example, if you have a low temperature simulation, then 1 femtosecond time step may be accurate enough that you can get sufficiently good simulation results. Of course, within this region, you want to make sure that your system is being simulated correctly, and so you typically pick the highest time step that you can while maintaining the numerical accuracy that you require. So the default is probably 1 femtosecond, but if you are unsure about the stability of the numerical algorithm, then 10 to the minus 16 seconds is probably a better choice. Okay, so we've now outlined the different integration methods that you can use in the atomistic spin model. And if you do a precise comparison of the two methods, you can find actually that you get the same results as you might expect. So here is a calculation of the temperature dependence of the magnetization, comparing a Monte Carlo algorithm also with the Landau-Dirichlet-Gilbert equation. So this calculation was actually quite tricky and used 10 to the minus 17 seconds in the Landau-Dirichlet-Gilbert equation to get a converged answer for the Curie temperature. So in general, Monte Carlo methods are much better for calculating equilibrium properties, for example, Curie temperatures, susceptibility, specific heat, that kind of thing. Whereas obviously LG is great for dynamic processes such as hysteresis loops. But in the limit, they do kind of converge to the same thermodynamic properties, so you can extract then the macroscopic Curie temperature that you get from the system. So all these methods are actually implemented in the Vampire software package, and so the other tutorials here will kind of outline how you can use the Vampire code to do simulations of atomistic systems and calculate magnetic properties and dynamics.